Hi, this is an example problem from chapter 16 on waves and sound. This problem deals with the intensity and the intensity level of sound waves. Pause for a moment to read the problem. So you can see in this problem, there's a picture there below. There's two people and they're watching a firework. They're at different distances from the firework. In part A, we are asked, what is the sound intensity detected by a man who is a distance 160 meters away from the explosion? In this type of problem, there's two different words that are similar but have different meanings. One is sound intensity. Now, sound intensity is a physical property of the wave. It's how much power is watts, right? Joules per unit second, and the intensity is the power per unit area. So whenever you have sound intensity, you're going to see units of watts per meter squared. This is different than the sound intensity level, which is a subjective experience of loudness for a human, and that has units of decibels. Oftentimes we just call this the decibel level, so we don't get confused. Now for part A, we're dealing with sound intensity of the man, and so for part A, the definition of sound intensity, I, the sound intensity, is equal to the power generated by the source of the noise, of the sound wave, divided by the area about which it's spread. Now for this firework, the source is right here, and so this is the generation of the power, but as time goes on, this is going to spread out further and further in a spherical area as it approaches those people. And in that case, the area here is given by the area of the sphere, which is 4 pi times the radius of the sphere squared, assuming that there's no reflections, which that is what it says in the problem here. So we can use that. Now we want to calculate the sound intensity I for the man. We don't know what R is for the man. We don't know what P is for the man, so that's a difficulty. However, one thing we can do is we can relate the man and the woman, because if we think of these three variables here, intensity, power, and area, for the man and the woman, one of those three variables has the same value, and that's P, as I showed over here, because P is the source, and it's the same for both the man and the woman. So if I want, I can go ahead and start by setting the power for the man equal to the power for the woman, and then we can go ahead and calculate I for the man. So for the man, we have, let's see, power in this case from this equation. Let's see here. If we want to go ahead and calculate power here, it's going to be power is equal to 4 pi r squared multiplied by I. Right? So let's go ahead and put those in. So for the man, we've got 4 pi r man squared times I man is equal to, for the woman, same thing, but for the woman. Now we can cancel out the 4 pi, and we can solve for the intensity heard by the man. It's equal to radius of the woman times the intensity of sound where the woman is at, divided by the radius of the man squared. And in fact, we can go ahead and simplify a little bit. So here's the sound intensity that the woman experiences and at the location of the woman, and here is the ratio of the two radii. We can go ahead and do that. That's mathematically good. So when we plug in our numbers here, for the woman, we have a sound intensity. This is the woman, I2, R2. We have a sound intensity of 0.1 watts per meter squared. That's I for the woman. And then the radii for the woman, it's 640. For the man, it's 160. and then we need to square that. Of course, the meters cancel out. And we come up with a intensity at the location of the man, which is 4 times squared 2, that becomes 16, right? So that's going to be 1.6 watts per meter squared for the man. All right. Now let's look at part B. Part B deals with sound intensity level, which is the subjective experience of loudness that these people are experiencing. And that's measured in decibels. So for part B, we're going to go ahead and we're going to calculate the sound intensity level experienced by the man and separately by the woman as compared to the threshold of hearing. And I notice a typo here actually. This should be equal to I0, not I2. This is I0. And that's how we indicate the threshold of hearing, which is the intensity of a noise that is just barely perceptible to human ears. And that is equal to 1 times 10 to the minus 12 watts per meter squared. Now here's the equation for calculating the intensity level beta in terms of decibels. And in fact, it is a comparison of 2 sounds. So in this case, we're going to compare the man to the reference of hearing here, and the woman to the threshold of hearing here. So the way to write that is going to be like this. For the man, we're going to write beta of the man compared to the threshold of hearing. That's going to be equal to 10 decibels times log. Now this is log base 10. And it's the ratio of the the 2 sound intensities. What is present where the man is located and what the reference value, the threshold of hearing is. So if we go ahead and plug these in, we're going to have 10 dB times log base 10 of, for the man, 1.6 watts per meter squared divided by the threshold of hearing, 1 times 10 to the minus 12 watts per meter squared. And again, this is a ratio, so this is nice. The units are the same, they cancel out. When we plug this into our calculator, the loudness in decibels of the man is equal to 122 decibels compared to the threshold of hearing. Now for the woman, we're going to do the exact same thing. So beta for the woman compared to the threshold of hearing, well, it's going to be 10 decibels log 10 on the bottom again. Threshold of hearing, we can ignore the units for a moment because we know they'll cancel. They're the same. And for the woman, the intensity was 0.1. And when we calculate this, we end up with the value 110 decibels loudness observed by the woman compared to the threshold of sound. Now for part C, we're asking, what is the sound intensity level experienced by the man compared to the woman? Well, we can go ahead and directly use the same equation if we want. Now we're going to calculate beta for the man with respect to the woman. 10 decibels times log base 10, the intensity for the man compared to the intensity for the woman. That's what this means. And when we put those numbers in, we're going to have for the man 1.6, and for the woman it's 0.1. And putting that into the calculator, we come up with the value 12 decibels louder for the man as compared to the woman. Now look at this. Why don't you take this number here and subtract from that number? You also get 12 decibels, right? That's no coincidence. In fact, the log property is a special one such that if we take the decibel level of the man with respect to the woman here, it's the same thing as if we take the decibel level of the man with respect to the threshold of hearing and subtract from that the decibel level of the woman with respect to the threshold of hearing. Of course, that's 122 dB minus for the woman 110 dB, which is also 12 dB. So there's a couple ways to do this.